So in your video last night, I did a vector application problem that was talking about an airplane. And the reason that we're going to do a bunch of different airplane problems is because those are the most, I think they're the most straightforward, and they're also very common. So if you were to see a vector problem, vector word problem on your final exam, which I wouldn't be surprised if you did, I'm thinking you probably will see one. If they gave you one, it would probably be a plane problem. Okay, so that's why we're going to go over that. So if you want, you could maybe rip off the front page because we can use that to kind of like guide us through the problem. You don't have to rip it off, but it could be beneficial. So if we look at the airplane problem, what was the very first thing we did on the notes? First thing. Yeah, we found, so this time it had a jet instead of an airplane, but the first thing we wanted to know is what the angle was that the airplane or the jet was flying. That's the first thing we wanted to know because they gave it to us as like a compass measurement instead of like a math calculator measurement. So I'm going to read this problem. It says an airplane has an airspeed of 500 kilometers per hour and it is flying north 45 degrees east. So the very first thing I'm going to do is I'm going to figure out what the angle is that my plane was flying. So north, I said that weird, north 45 degrees east would be this way, right? But when we measure angles, we measure them this way. So what angle does that mean for us? 45. So coincidentally, it happens to be the same. Okay. We also need to know what the magnitude of the airplane is. Can anyone tell what that is? 500 kilometers. There's the magnitude of the airplane. Okay, so now what we do, now that we have the angle and we have the magnitude, is we go ahead and we write the vector for the airplane. So using that angle we found, the 45 degrees, and using the magnitude, we're going to do exactly what we did on that worksheet yesterday, and we're just going to write this down. Sound good? Okay. So I'm going to say that the vector of the airplane, I'm using a little a for airplane, is my magnitude times cos 45. Do you guys like the i's and the j's, or do you want to do component form? I's and j's? Okay. Now you can do component form if you want. It doesn't make a difference. It just is your comfort. So 500 cos 45i plus 500 sine 45j. So that vector is done. Next, what do we do based on our notes? We need the vector of the wind. So if we look at the problem, it says the wind velocity is 60 kilometers per hour. What did they just give us? Magnitude. So I'm going to circle that. That's my magnitude. In the direction north 30 degrees west. Okay, so I'm going to draw this. North 30 degrees west is this way. So that's 30 degrees, which means if I think about this in my calculator, what would my calculator want me to use? 120. Okay, so now I'm going to say the vector of the wind is what? Plus 60 sine 120j. Okay. Now it says what? What did we do next on our notes? We found the vector of the plane, the vector of the wind, and then what did we do with those vectors? We added them together because we wanted to find the resultant, which is the result. Okay. Isn't that crazy how they named it that? It's almost like they knew. So I'm going to say vector of airplane plus wind. And how do I add these together? I's and j's. So I'm going to say, I'm thinking about it as like these are kind of like x coordinates and y coordinates. I'm going to combine my x's, I'm going to combine my y's basically. So I'm going to say 500 cos 45 plus 60 cos 120. That's the number I'm going to have in front of I. And then 500 sine 45 plus 60 sine 120 is going to be the number in front of J. Okay. And then after I had written that on the notes, what did I do next? I put it in my calculator so I could see what my decimals were. Okay. So make sure you are in degrees. And then 500 cos 45 plus 60 cos 120. And so I get 323.553i, and I'm going to store that in my calculator as x. You can store it as whatever you want to, but x will be kind of nice. And then I'm going to type in the same thing, but with sine instead of cosine. And then I'm going to store that in my calculator as y. So this vector represents the flight path that the plane is actually going. So the plane is trying to go 500 kilometers per hour, like when the pilot is putting his foot on the gas pedal, that's what he's trying to do. But the wind could be pushing it along and making it go faster, or the wind could be pushing against it, making it go slower. Okay? So if you think about it, if your plane is flying this direction and your wind is pushing that direction, do we think our plane is going to speed up or slow down? Probably slow down a little bit. We got the wind pushing against it. Okay, so let's go ahead and figure out what the actual speed of the plane is. What word did we call these two in vector vocabulary? Magnitude. So what we need to do now is we need to find the magnitude of the airplane and the wind together. All right, and that's the speed formula. So if you're going to find the speed, you're going to find the magnitude. And that's why the next thing we did in the notes is we took the square root of x squared plus y squared. Okay? So now I'm going to say speed is square root of 323.553 squared plus 405.515 squared. But in my calculator, I'm really just going to type square root of x squared plus y squared. So we got 518.777. Did I type something wrong? Oh, I was looking at the wrong problem. All right, so it actually made it speed up a little bit, which I guess is kind of interesting, but I guess it kind of works because the wind is not that strong. It seems a little weird, but I guess it kind of works. So let's go ahead and draw. What we're going to do is we're going to draw a picture of this. So, and I think that once we draw the picture, it will probably make a little bit more sense. My guess is it would have slowed it down too. Okay, so what we need to do is we need to draw a vector that goes the direction 45 degrees, or this one, I guess, the direction 45 degrees, but has a length of 500. Okay, so we're going to draw a vector that's smack dab in the middle, and it's going to be pretty long. Does that make sense? That's the vector of our plane. And then from there, I'm going to pretend that I have an x and a y axis right here, where I ended. And I'm going to draw a vector that has an angle of 120 degrees, but it only has a length of 60. So if we think about this one being a length of 500, the next one's going to be a length of 60, the next one's going to be quite a bit shorter. Does that make sense? Okay, so we're going to draw, here's our 120 degree angle, something like that, and then 60 is going to be pretty short. All right, so let me zoom in. This is our vector for the airplane, going 45 degrees with a length of 500. This is the vector of the wind, going 120 degrees with a length of 60. And then our resultant would be right here. So now if we look at that, does it make sense that it went a little bit faster? I can see now when I draw it that my resultant vector is a little bit longer, which means that it has a higher speed, because the length of the vector would represent speed. All right, so what we're going to predict here is that if the original angle was 45, the angle that we get should be a little bit more than 45, right? A little bit more? Okay, so let's go ahead and find the angle. The way that we're going to find this angle right here, theta, is we have to consider this vector that we have, our resultant vector, and we have to think about, like we did on our warm-up, having that x value and that y value, right? So we're going to say tan theta equals the y value of that resultant vector divided by the x value of that resultant vector, and that's how we're going to find this angle that it makes. Does that seem reasonable? Okay, so we're going to say 405.515 divided by 323.553, but in my calculator I'm really just going to type y divided by x. So in here I can do tan inverse because I'm thinking about getting that theta by itself, y divided by x. All right, and I get an angle of 51.414 degrees, which fits kind of that picture that we looked at, that our angle would be a little bit bigger than 45, but still quite a bit less than 90. Okay. All right, and then when we are done with this angle, this is the calculator angle. So now what do we have to do with that? Are we going to give them the calculator angle as an answer? Now we're going to convert it back into the compass measurement, okay? Now these compass measurements were a little different. One was northwest, one was northeast, and so we know that when we write our answer, we're going to do north something. I'm not going to write it in bearing. I'm not going to write it from south. I'm going to write it in the way the context of the problem was written. So this is going to be north something. Is this going to be west or east? East. Okay, so it's north something east. And how are we going to figure out what it is? Subtract it from 90. So I'm going to say 90 minus this answer is 38.586 degrees northeast. And that's why you did the assignment yesterday. Does it make sense now why we did that ahead of time? I wanted you guys to practice that stuff so it wouldn't confuse you today, now that we're like putting all the pieces together. So when you're done with this, you need to write a sentence, because today we actually do need to be able to interpret like the math that we did and know that our answer makes sense. So your sentence is going to say, the ground speed of the plane is 519 kilometers per hour. I'm going to round to a whole number, because we're probably not going to have this 3 decimals of accuracy when we do it. And then I'm going to say in the direction north 39 degrees east. So when you do your paper, I want to see that you are capable of getting 3 decimal places of accuracy. But when you write it in a sentence, I want you to round to the nearest whole number. Make sense? Okay. So we're going to say the ground speed of the plane is 519 kilometers per hour in the direction north 39 degrees east. So if we think about it, this is basically a 5-step process. If you're doing a problem with the plane and wind, which is most of the problems you'll be doing. The first step is to find the vector of the airplane. The second step is to find the vector of the wind. The third step is to find the resultant vector, so add your vectors together. The fourth step is to find the speed of the resultant, which is the magnitude of the resultant. And then the fifth step is to find the angle of the resultant. Okay? So you basically have a 5-step process, and that 5-step process works for most of these problems. Sometimes they get a little weird on you, but most of the time it will work. Okay? All right, now we're going to flip back to the front page, and we're going to add a little note to ourselves on the top. When you do the part where you say tan theta equals y divided by x, you have to type tan inverse to get an answer, right? And this is going to remind us of the unit that we learned before about inverse functions. Do you guys remember what quadrants you're allowed to have a tan inverse function in? 1 and 4. So the calculator is only going to give you answers in quadrants 1 and 4. It will never give you an answer in quadrant 2 or 3. Okay, so I'm going to write on my paper, calc only gives quads 1 and 4. That's the only place it will give you an answer. That doesn't mean that that's the only place an answer belongs. That just means that's the only place your calculator can give you an answer. Okay? So if the answer is supposed to be in quadrant 2 or 3, do you remember what we have to do to tangent to get the next answer? Add 180. So if it was in radians, you would add pi, but we're in degrees, so we're going to add 180. Okay? So we're going to say for answers that should be in quadrant 2 or 3, add 180. Okay? So let's go back to the problem that we just did. This is why before you do step 5, you draw a picture. When I drew the picture, I could see that my answer was in quadrant 1, so I knew that the answer my calculator gave me was going to work. If I drew the picture before I did number 5 and I saw that my answer should be in quadrant 2 or 3, then I know that when I get this part right here, I should add 180 to it before I move on. All right? So when I look at number 5, I have to draw a picture and see what quadrant the answer ends up in. Right, Christian? I can actually see it better under the table than on top of the table, just for future reference. So if it's in quadrant 1 or 4, that answer's good. If it's in quadrant 2 or 3, you're going to have to add 180. Make sense? It doesn't happen on every problem. It happens on half of them, right? Because half the time you're going to be in those 2 quadrants. Make sense? Okay. So I'm going to let you guys work on that. The answer key is on the board, and then if we need to do one together later, we can. There are not enough problems to keep you busy all period, so at some point you're going to switch over and work on the review. Yes, ma'am. Yes. This is like there being, because you see how it says bearing south 30 degrees east. So in a case like this, you would ignore the fact that it used that word, because they could say, it's kind of like when you're driving and it says bear right on this road, bear left in this road. So they can say that you're bearing as in you're going that direction, which is different than saying it's an angle that starts with bearing. So if it says bearing south 30 degrees east, ignore the word bearing right there. It doesn't do anything for you. Just use the south 30 degrees east part. Yeah. All right. In your packet, put an X through number 11. I know you're devastated, but you're not going to do that one. So skip number 11. I think you can still do 13 because it's very similar to the airplane problems, but you're also going to skip number 14. So skip 11, skip 14. That means that you only have like 5 problems, I think, to do. 4. So it shouldn't be bad. Sound good? Yay, we're so excited! Okay.